Okay, I see everybody's joining in now. I'm just going to go ahead and start the introduction. So hi everyone, welcome to the Essex Seminar Series. My name is Kazi. I'm going to be moderating our seminar today. Usually, if you are a seminar series regular, you will know that usually John does this spiel. He's unavailable today. So I'm filling in. I want to give a warm welcome to Professor Karen McKinnon from University of California, Los Angeles. So her talk today is titled Heat Extremes in a Warming World. The seminar will be recorded and the video will be posted on our YouTube channel this week. At the end of the talk, we will have a Q&A session in which I invite you all to ask your speaker questions by unmuting your microphone or via the chat. You can also leave questions throughout and then we'll just read them all off at the end. So a little bit about our speaker. Karen McKinnon is a professor of statistics and the environment at the University of California, Los Angeles. Her research sits at the nexus of climate change and statistics and is aimed at improving our understanding and prediction of climate extremes, variability, and change. She is a 2023 Kavli Fellow, a 2021 Packard Fellow in Science and Engineering, and has served as an advisor for both city governments and private companies regarding climate change. Professor McKinnon received her BA, MA, and PhD from Harvard University, as well as a Master's of Science from Victoria University of Wellington. She was an advanced study program postdoc at the National Center for Atmospheric Research and Applied Scientists at Descartes Lab before joining UCLA. Now I will hand it off to our speaker, Professor McKinnon. Please proceed with your talk. Thank you.
Great. Thank you so much, Kazi, for the introduction and for hosting me today. And thank you, everyone, for spending a little bit of time with me this morning to chat about heat extremes. As Kazi and I were chatting about at the beginning, just informally, this has obviously been another pretty record-breaking summer for a lot of folks. And so this is, I think, both scientifically interesting and probably feeling increasingly socially relevant as we experience these extreme summers. All right, so I don't really need to, in some sense, remind anyone that we are living during a time of rapid global warming, but I do like to first put up this slide just to point out that when we think about kind of global mean temperature change, and that's shown here in this light blue line from 1880 to the near present, most of that actually is a function of how ocean temperatures have changed, which is shown in this blue line. And for reasons that we understand reasonably well scientifically, land temperatures warm about 60% or so faster than ocean temperatures in response to increasing greenhouse gas emissions. So if we focus instead on this yellow line, which is just looking at how land temperatures have changed over time, I think it really highlights, how rapid this global warming that we're living through is, and particularly how that's amplified over land. So over land, rather than that like 1.1, 1.2 degrees Celsius temperature measurement you might have in mind for global mean temperature, we've seen about 2 degrees Celsius or 3.6 degrees Fahrenheit warming over land since 1880. And this plot was made before the recent year of 2023. So I just want to point out that global mean temperatures in 2023 have really been, kind of beyond that time series, behind that linear trend that we saw in the previous plot. So this is from Climate Reanalyzer, and this is showing global mean temperatures, not just land, so both of them. And from 1979 to 2021 in the gray, 2022 in the orange, and then 2023 in the black. And as folks in this call may be well aware, our global mean temperatures in 2023 have really kind of jumped off this cliff and far exceeded during the Northern Hemisphere summer values that we've seen before. So we are really observing, pretty rapid climate change at this time. And the largest climate change impacts and how we really feel climate change, really tends to come out of those extreme events. And so the National Oceanic and Atmospheric Administration most months makes these maps of significant climate anomalies and events. This is a recent one from August 2023. And what you can see is that most of these events in both the Northern Hemisphere where it was summer and in the Southern Hemisphere where it was winter are really coming up as these little thermometer events, aka very extreme temperature anomalies. And so we're seeing, this climate change signal overall, and that's really manifesting in a number of these major extreme events. So a kind of basic question that really motivates a lot of my work is how and why are heat waves changing in a warming world? And in one sense, this is a very easy and obvious question. So as the global mean temperature is warm, we're going to have more heat waves. They're going to be more extreme. They're going to be longer. That's true in a very, very basic sense. But I think there are still a lot of open questions about exactly how heat waves are changing. Are they, following land temperatures overall? Are they amplified? And why are they changing in certain ways? So today I want to cover three pieces of work generally on that theme. The first is actually talking about just a framework for how we talk about changes in heat extremes. The second is talking about a recent very extreme event, the 2021 Pacific Northwest heat wave, and kind of how unexpected was that type of extreme event given climate change. And then finally, in the third section, I'm going to move beyond thinking about heat waves just in terms of temperature to bring in this humidity component and show some results on how we're actually seeing some unexpected decreases in humidity on hot days in dry regions. Okay, so I want to begin with just a framework for how we talk about changes in heat extremes. And this kind of framework was published in my work in 2016, but we're actually now updating that. And so that's why I'm bringing it up now. And also because I think it's important as, we as scientists do a range of studies about heat extremes to really try to do studies that are as kind of clear and consistent across studies. So in this first section, I am kind of advocating for a certain way to talk about heat extremes, but I hope that why I've taken this approach will be clear after the next couple slides. So what I have shown here are June, July, August temperature anomalies at an ERA5 grid box pretty close to the University of Maryland, who's hosting the talk today. And they're from 1940 to 1980. So imagine that as some kind of, middle of the century, doesn't have the current climate change signal on it. That's this blue histogram. And what I've added to this blue histogram is the 90th percentile of the temperature anomalies, as well as the maximum that was observed over this historical period. And then what I've done is I've just added here a kind of made up climate change signals. This isn't actually kind of present day data, but just a case where if you imagine that what climate change has done is just shifted all of these temperatures at the University of Maryland warmer by 2 degrees Celsius, which is about how much land has warmed overall since 1880. And so what you can see is that, this whole climate change signal could be described by a single number, because I've simply defined it as everything is getting warmer by 2 degrees Celsius. And we could kind of describe everything that's happening across the whole distribution by this single number. However, in the literature, people often use a different type of number, which is the change in the probability of certain type of extreme events. And so I've quantified that here as like the probability in this kind of future made up 2 degrees Celsius climate change scenario divided by the probability in the past. And what's shown on the x-axis here is percentile. And so in each one of these points, we're showing the probability change of exceeding a certain percentile of an extreme. So the 90th percentile, and then up to the 99th or the 100th percentile. And what you can see here is that kind of that simple linear shift that we had in the previous plot that was explained by that single number now leads to this nonlinear behavior in the probability of heat extremes. And so, you increase the probability of an event greater than the 90th percentile by 2.5. You, of course, basically infinitely increase the probability of something greater than the historical maximum. And you can see why by just flipping back here as you get to increasingly small probabilities historically. The same 2 degrees Celsius shift can amplify those probabilities essentially in arbitrarily high amounts. Now, this, importantly, I should say, is not a new result or anything unsurprising. This has been obviously known for a long time. It comes from the basic statistics. But nevertheless, we still often see in the literature, these types of metrics. And I just want to point out how, they kind of take a simplified climate change signal and, in my opinion, make it a little bit more complicated. And then even more importantly, how that nonlinear behavior looks is actually a strong function of the underlying distribution of temperature. So here I just have two made up temperature distributions. You can imagine that past distribution's in the blue, and I've shifted it by 2 degrees Celsius into the red. This one here is a so-called negatively skewed distribution. You have more weight in this lower tail, and this one is a positively skewed distribution. So again, this is kind of the simple shift behavior. Everything's getting warmer by 2 degrees Celsius. But if you look at it in terms of the changes in the probability of a very extreme event, you see very different behaviors. So in our negatively skewed case, you get these, very large amplifications of those hot extremes. Whereas in our positively skewed case, you don't see such a large amplification in terms of this other metric. So I would argue that this kind of is a more confusing picture that could be simplified by just looking at how this distribution is changing across each percentile. In this case, it's kind of a simple shift towards 2 degrees Celsius warmer. So in general, what I'm going to talk about in the coming slides is how our temperature distributions have changed generally. And you might think that a good way to do that would be to look at changes in their mean and their variance. That's what we could do for a normal distribution. If it's just Gaussian, that fully describes the full distribution. But daily temperature data, which is relevant for extremes, tends to be non-normally distributed. That's shown here with the skewness and excess kurtosis of daily temperature distributions at stations. That's each one of these dots. It's a station measuring temperature for daily maximum temperature. The details here aren't super important. Skewness, again, is basically do you have more weight in your positive or negative tail. Excess kurtosis is you have more weights in your tail compared to a normal distribution. But the relevant thing here is that anywhere that these dots are not kind of a gray color is a case where we have significant non-normality in our distribution. And what that means is extremes are going to be more or less likely than a normal distribution, depending on the values of these parameters. I'll also highlight here, because I love working with station data, if you haven't looked at station data for where we're actually measuring these important climate quantities around the world, you'll notice that these dots are not equally distributed. And we actually have, I would argue, pretty fundamental limitations in where we've been measuring critical climate quantities historically and also in the present for us to understand climate change. Okay, so that's kind of, in my opinion, one of the challenges of talking about heat extremes. What I'm going to argue here is that a really helpful tool to understand how temperature distributions are changing is something called quantile regression. And what quantile regression is a tool that allows us to understand the trend in different quantiles of the data, like the median for the 50th quantile, or say the 5th or the 95th percentile of data, as a function of various types of regressors. So say it changes as a function of year or global mean temperature, or whatever kind of variable you're interested in. And the reason I think this is helpful is that it can allow us to really clearly and quantitatively distinguish changes in temperature distributions and temperature extremes from those that are just explained by that simple shift behavior I showed before versus other changes in shape. So in this schematic, you can imagine that this is some temperature distribution historically. And how I've made the schematic is such that as we go through time or increase global mean temperatures, this distribution is just shifting to warmer and warmer values, but its shape isn't changing. So all of the quantiles are increasing at the same rate. And I want to just contrast that to a case where maybe you have a more complicated type of change where your middle of your distribution is changing in the same way, but perhaps your distribution is getting wider. And so you amplify the probability of these hot extremes and damp the probability of these colder extremes, as an example. And so this tool can kind of allow us to separate between this simple shift behavior and these more complicated changes in shape. So we used that framework originally back in 2016 to try to get an initial metric of how summer temperature distributions were changing. And I'm going to show the results from that first and then show a slightly updated version that is currently in prep. So in this historical analysis, we were using this GHCND station data, those same dots I was showing on the prior plots with skewness and kurtosis, and looking at daily maximum temperature. We looked only at the Northern Hemisphere midlatitudes. That's where basically we have a lot of stations available. We tend to not have much station availability in the tropics in the Southern Hemisphere. We were looking at the 60 hottest days of the year. And in this older analysis, we were just looking at a simple linear trend from 1980 to 2015. So that certainly has a certain number of limitations. We didn't, for example, consider the role of internal variability or other forcings that were nonlinear in time. So this is more or less what we found. What's shown here are trends in the 5th, 50th, and 95th percentile of summertime temperatures over that 1980 to 2015 period. Each of these dots is, again, one of those weather stations, and trends identified as significant in this paper are in the bigger circles, and not significant are in the smaller circles. The first thing I want to point out is basically how similar each of these maps are. And so what we're seeing is that more or less there's the same general structure that's emerging in trends in lower, median, and hotter summertime temperatures. There is, however, substantial spatial structure in all of these maps. So for example, greater warming in this kind of Central European region, actually a cooling signal that is real and probably due to both aerosols and changes in land use that's happening more in this Midwestern US region. So we see kind of regionally variable temperature trends, but pretty large similarities across percentiles. And what that suggests is that we're mostly seeing that type of shifting behavior that I've been talking about so far. Now, in this paper, we actually extended our analysis to look at trends really across the distribution, not just these 3 percentiles, and then took the behavior across all of those trends and summarized them by projecting onto 4 orthogonal basis functions. And so each basis function allowed us to summarize the spatial structure of a certain type of change in the temperature distribution. So the first basis function is just that simple shift behavior that I've been talking about a lot. So where every percentile is kind of warming the same amount, and you can explain what's happening at the upper percentiles by looking at what's happening in the middle of the distribution. And that pulls out that kind of spatial structure that you've seen in all of those other maps, and explains, importantly, about 88% of the variance in the data. So historically, we've mostly really been seeing this kind of shifting behavior. The next basis function is about if the distribution has shifted or contracted. Shifting is in red and contraction in blue in this plot. And you see places where there is certainly some of that behavior going in either direction, either a stretching or a contraction. But overall, it explains only about 8% of the variance in the data. And then the remaining 2 basis functions have more nuanced changes related to the skew and also how heavy those tails are. But we see that they may be locally important, but again, explaining a pretty small amount of variance overall in the data, about 2% and less than 1%. So overall, this analysis said, mostly what we're seeing in summertime temperatures is basically this relatively simple shifting behavior. And since we really care about extremes, what's shown here is the residual trends in those 5th, 50th, and 95th percentiles. We can probably focus mostly on this upper one here. The residual trends after accounting for that shifting behavior. So in this map, what this is showing is how much the 95th percentile has warmed more in red or less in blue compared to what we'd expect from just the whole distribution shifting. You can see there's some structure here. So for instance, this band across kind of central Eurasia is certainly showing maybe a little bit of an amplification of those hot extremes. But if we compare to our original trends, which I've just flipped to here, we can see that really most of that structure is being explained by this shifting of the distribution. Okay, so as I mentioned, this kind of is an old study at this point. It was 2016 when we published it. We were only looking at 36 years of data. We were assuming linear trends. And a lot of the summers that we have seen recently seem to have been very, very extreme. And so the reason that we're now revisiting this type of analysis is to ask if that story has changed given recent summers, and also some advances in both our statistical modeling and our understanding of the climate system about the role of internal variability. So this is now basically work in prep. It's very preliminary, but what I'm showing here are, again, trends in daily maximum temperature, now at this point using ERA5, although we'll also look at station data, looking over a longer 1940 to 2023 period. So we're including this most recent summer we've just had, and looking at trends in the 50th and the 95th percentile of daily maximum temperature. As a function of, rather than time, we're going to be using a low-pass version of global mean temperature that's shown in the blue time series on the right-hand side. We're using this rather than time because it's been shown as a more effective way to pull out the climate change signal versus internal variability, and also allows for some of the non-linearity of climate change that we've observed when you go all the way back to 1940. I'm only using June, July, and August global mean temperature, not because that's a better metric, but rather because this year we haven't yet observed the whole year, so we don't have the full annual global mean temperature. And we're also allowing for Nino 3-4 to influence our temperature distributions to kind of separate out an El Nino versus a climate change type of signal. And in future work, we'll also be incorporating aerosols. So this is what you see in this updated analysis. This is showing, again, the trend here in the 50th percentile and the 95th percentile of summertime temperatures in ERA5. And I'll first point out, again, if you compare these 2 maps, they look pretty similar to each other. So largely what we're seeing is that hot days are basically following the median. We seem to mostly be still seeing this overall shifting type of behavior. But if you're, again, thinking about, how is that possible when heat extremes have seemed so extreme? I'll just emphasize that there's a lot of spatial variability and some places have warmed a lot. So let's focus, for instance, on this Western Europe and Mediterranean region. This color bar is indicating a value in excess of 3 degrees of warming per 1 degree of warming in global mean temperatures. And we've seen over this period from 1940 to 2023 about 1 degree warming in these global mean temperatures. And so this is a region where you've had about 3 degrees Celsius of warming over since about 1940. And so there may not be this amplification of heat extremes, but the shift in summer temperatures have been quite substantial. I'll just say anything that's in red is a place that is warming faster than the global mean. Anything that's in gray is a place that has a positive trend, but is warming slower than the global mean. And anything in blue is a place that actually is cooling. And then what's shown in this last map is just that difference between the 95th and the 50th percentile. And so places that are red are places where there is, greater warming empirically. I haven't assessed significance here of that 95th percentile, and blue is where there's been less warming of that upper tail. So we actually have a lot of work to do, I think, to understand this map, specifically to understand which of these differences are just explained by sampling of internal variability. We always are going to expect some noise in our trends because internal variability is so large. And in cases where we do believe that there might be a real signal of either amplification or damping of these hot extremes, what are the physical mechanisms? So I won't have time to talk about it today, but my group is thinking a lot about land-atmosphere interactions and how those can amplify or damp extremes. So hopefully in the next couple of years, we can come back with a little more information about what we expect to see from a basic climate science perspective in terms of changes in extremes. But overall, I would say in most cases, the dominant signal, again, is this shifting behavior towards warmer temperatures. Okay, so, then we, thought about this study, and then we ended up seeing a lot of, it seems, very, very extreme events. And the question that it raised in our head was, given recent climate change, and if we are just seeing the shifting in summertime temperature distributions, can we really explain these very, very extreme events that we've been seeing? And specifically, we focused on the 2021 Pacific Northwest heat wave, which is shown here in an image from NASA. This happened at the end of June in 2021, and we just had dramatically record-breaking temperatures across primarily Washington and British Columbia, a little bit in Northern Oregon as well. And in some cases, these exceeded previous anomalies, by previous records by 5 or 6 degrees Celsius. So it was a case you just had this enormous jump beyond what we've seen before. And the question is, can you really explain these types of events if we are only seeing this, shift in summer temperature distributions? So the first thing that we did is we focused back on this region specifically and asked, again, does the station data kind of enforce the same conclusion we've seen globally, where we're mostly just seeing shifts in distributions? So just to contextualize you, this is that same Pacific Northwest region. Here's Oregon, Washington, British Columbia. This box is more or less our domain of study. And each one of these locations or dots is a station that had temperature measurements. There's actually 3 data sets going into this plot. Global Historical Climatology Network, which we have data back to 1900, but really none in Canada, mostly in Washington and Oregon. Environment Canada, which goes back to 1925, but is only available in southern Canada. And then we supplemented that with the ISD data set, which is available beginning in much shorter records, basically beginning in 1973 in the US and 1977 in Canada. The reason that we've used this last data set is because, especially in Canada, we had very few, actually we had 0 stations in this northern part of the domain where the heat wave was pretty substantial, and we wanted to get records that kind of included that northern part of the domain. But the reason I'm emphasizing this is that we actually don't have super long station records for this whole domain, and that is going to affect what I'm about to talk about with trends. So we again took this quantile regression analysis. We asked how are temperatures during this early summer period that the heat wave happened during, how are they changing with increasing global mean temperatures? And that slope or sensitivity is shown here in the colors for the 50th percentile. Anything that is a circle is a place where the trend is significant. Anywhere that is a pentagon is a place that we identified it as not significant. Although I will emphasize we haven't done spatial modeling. If we had done some spatial modeling, shared information across stations, we might find stronger significance in some of these locations. So what you see overall is, of course, we've generally seen global warming. With these shorter records especially, we often don't actually find a significant signal, and that's mostly related to how short the records are. And then if we compare that to the 95th percentile, this is again those trends in those upper percentiles in temperature, we do in many places see overall, stronger trends over this period. However, if we assess the significance of the difference between the 95th minus the 50th, so do we see kind of a greater warming of the 95th? We overall actually found that none of these were significant, and that's again related to the fact that all of our station records up here are quite short. And so I think there's still some work to be done with, again, some spatial modeling to try to find some greater significance there if it's present. But this is a pretty noisy metric. And so overall, in the station data, we mostly just see a consistent shift signal. We're not seeing the amplification of those hot extremes. So we've kind of confirmed that in this region, we're still mostly seeing shifts in summer temperature. And I will say that just qualitatively, there's similar results with this updated ERA5 analysis I was just discussing. There's even maybe a damping of the 95th percentile in much of this region, and maybe a very, very small amplification in British Columbia. But overall, we're still seeing that signal with a different data set. So if we assume that climate change, again, has mostly shifted the temperature distribution, do we expect that the climate system, can produce heat waves as large as the 2021 event? That was really the question that was at the fore of our mind as we did this study. And the question was motivated by this interesting study that came out from the World Weather Attribution Group that's now published in our system dynamics by Philip et al. And what they found in this study is that they took a look at maximum temperatures in this region as a function of global mean surface temperature. And if you look before 2020, there are all these blue dots, and they can be very, very well explained in their behavior by fitting a standard statistical model for extremes, which is a generalized extreme value distribution. However, if you looked at the 2021 data, you had this huge outlier here that could not be explained by the standard statistical model. And indeed, in their initial modeling, it suggested that the probability of this event was literally zero. And so given the historical data that we would never have expected that what we saw in 2021 could occur. And so that kind of raises the question of, is this really coming from a different set of processes, a different distribution, or can we understand that these very extreme events, can be produced by the physics of the climate system? So to start to understand how these extreme events can happen, we actually took a look at the climatological distribution of temperature in these locations, and specifically whether each station before 2021, so not including the 2021 data, tended to be negatively skewed or positively skewed. So a lot of stations over land have this negative skew behavior where your kind of upper heat extremes are a bit limited. But stations here in the Pacific Northwest, where you tended to actually have the largest temperature anomalies, overall have this positive skew behavior. And what this means is that you have conditions, just climatologically in these locations, where even though maybe your overall temperatures tend to be somewhat moderate, you can produce these very large extreme events, and with kind of the the physics that are controlling the temperature at that location. And indeed, what we found, if we compared what the climatological before 2021 estimate of skewness was at these locations to the temperature anomalies during the heat wave, there was a pretty strong monotonic relationship where stations that had stronger evidence of positive skewness before the heat wave tended to have larger anomalies during the heat wave. So there's kind of processes that allow these stations to have unusually large temperature events, and we indeed saw that during 2021. I want to take a moment here just to talk about how or what I mean by these standardized anomalies, because it's quite important. So what's shown here are the standardized anomalies in standard deviation units. So that's the first point, that we're going to be considering everything in terms of how many standard deviations away from normal was it. That means that in 2021, for instance, these stations by the coast, they're have pretty small standard deviations overall, but their deviations during the heat wave were quite large because this is a place where temperatures are not usually that variable. So you had highly unusual events, even if the temperature anomalies weren't that large. But the other really important point is that all of the anomalies here are considered as anomalies from that kind of basic shift model. So we've already accounted for temperatures shifting towards warmer conditions due to climate change, and we're looking at anomalies from that type of shift. So we're really thinking about, conditional on historic climate change where things have warmed by a couple degrees Celsius, what are the anomalies on top of that? And we see that, again, if you had a larger climatological skewness, you tend to have larger anomalies during this heat wave. So to better understand what was going on, we then incorporated model simulations from the CESM2 large ensemble. We're using 50 members across that large ensemble that have the smooth biomass burning in them. And we first asked ourselves, does this kind of baseline behavior connecting skewness and how large temperatures can be at a given location hold across the climate model simulation? So I first want you to focus on just the smaller dots in this upper plot. Each one of these small dots is a single grid box in CESM2. Its location in the XY plane is its skewness and kurtosis. So do you tend to have up here a positive skew and positive kurtosis? That means high probability of extremes, or over here a negative in both, meaning a lower probability of extremes. And then the color of each of these dots is showing the largest extreme events across the historical period in the whole ensemble. So we're looking at around 8,500 years measured in standard deviation units. And what you can see is that as you go from purple to yellow, that's going from larger and larger extreme events, that there's a pretty clear and coherent behavior in this space where in order to get events kind of as large as what we saw in some of the extremes in the Pacific Northwest, you need to be in this positive skew, positive kurtosis type of space. And so, if you're up here and you climatologically have a large skewness and large kurtosis, it wouldn't be that unexpected to get something like a 5, 4.5, or 5 sigma event. Whereas if you live in a location with negative skewness and negative kurtosis climatologically, you're really not going to expect that you are able to produce an event that is as large as what we saw in the Pacific Northwest. And that's confirmed here, just looking at just the skewness part of it, so averaging over kurtosis, we see that as you have larger skewnesses, you can have a larger temperature anomaly in the model. Now, what's plotted on top of the model are these data points with the black outlines. These are all stations in the Pacific Northwest. Again, it's showing their climatological skewness and kurtosis before we saw that event. And then the color here is showing the largest temperature anomaly that you saw during the heat wave. And so what you can see is that there's a pretty clear mapping between what the climate model is doing and what the data is showing, and that these colors, basically match each other across the observations and the model. And that tells us two important things. First, that as we suspected, the climatological skewness and kurtosis are an important indicator of how extreme events you can get. And then it also shows, importantly, that the climate model can produce and does produce events that are as large as what we saw in the Pacific Northwest. And when this study came out, that was pretty important because some people were showing that they would look at a climate model and they simply could not get it to produce events as large as what we observed. If that were true, that would be kind of concerning. That would be saying that we're observing things in the real climate system that our climate models do not simulate. We actually found the climate model can simulate these, but I will emphasize that they're quite unusual. So in general, the observations and the size of those temperature anomalies were somewhat comparable to the largest temperature anomaly produced across the 8,500 years in the large ensemble. So if you want kind of an order of magnitude, it was kind of a 1 every 10,000 year type of event. And I think it's helpful just to visualize just in time series space what one of those events could look like. So this is, again, coming from the climate model, not from the observations. And this is just showing seasonal maximum of temperatures in a location in Central Oregon that did produce one of these major events. And so what you can see is that I haven't removed any climate change signal here. So CESM2 in this location actually doesn't warm very much until around like the 1980s. But somewhat out of the blue produces this enormous heat wave that is pretty comparable to what we actually observed. And so although they're unusual, we basically do see these events with only moderate levels of warming in the large ensemble. And future work in our group is really going to dive into these events and try to understand more about them, what they look like, what the physics are, and what if there are any precursors we can see that would help predict these type of very extreme events. Okay, and then looping back to the kind of that initial quantile regression analysis that I talked about, where we were saying historically, do we see an amplification of hot extremes? And if you remember, we said, overall, maybe there's a weak signal there, but it was very hard to pull out amidst the noise in the data. So with a large ensemble, we have a lot more data. We have 50 times more data that we can work with in this case. And so we again asked ourselves, does the large ensemble show that everything is just shifting with the mean, or do we see any amplification of the hot extremes? And what we found was pretty interesting. In CESM2 at least, and this may be a model-dependent result, we don't know yet. If you looked at events that were, moderately to somewhat extreme, mostly CESM2 just showed that everything was shifting with the mean. So if you accounted for the mean warming, you could explain what was happening at those most extreme events. But if you looked at the very extreme events, so in this case in blue, I'm showing events that exceeded the historical 99.9th percentile in temperature, and in red, events that exceeded the historical maximum in temperature up to 2020. We actually did identify significant trends in these very extreme events. So for instance, with the historical case, by definition, you never had these events before 2020. And then after 2020, we did see that there was often a non-zero probability of these events occurring. However, importantly, that probability remains quite small. So if you just take a look at this y-axis, we're talking about very, very unusual events. And so even if there is a forced trend in these very extreme events, it is also totally plausible we would never observe one again before 2100 because these events are quite unlikely. Okay, so our main takeaway on this is that the Pacific Northwest heat wave was primarily explained by climate change caused shift in temperatures that took us from basically this blue distribution towards a red distribution, where everything is just getting warmed by a certain amount. Plus, of course, basically the bad luck or the weather that can produce these types of tail events that we observed. However, this has basically led into current and future work. We started this analysis after the heat wave in 2021, but of course, things take a long time in science, and we ended up publishing it in 2022. And while we were working on those revisions, it seemed that there were a lot of events that were breaking records in a way that seemed somewhat similar to what we had just said was a roughly 1 in 10,000 year event. And so we kind of added a caveat to our paper that if similar events do start to occur with greater frequency than we expect, we do need to look at what's going on with our climate models and maybe do kind of a more complete analysis, not of single events, but rather what we're seeing across the Northern Hemisphere summers during 2022, and then I would argue now also during 2023. So that work is basically present and ongoing. Hopefully in a year or so, we can tell you what we found, and if we do see any different type of conclusion when we look more broadly, not just focusing on one single event. Okay, so the last thing I want to talk to you about is taking a little bit of a more nuanced look at heat waves and thinking about how heat and humidity are co-evolving and why they're co-evolving in certain ways. The motivation there is partly an impacts one. So we know that the impacts of heat extremes are strongly mediated by humidity. There's been a lot of focus on hot and humid conditions, which are of course quite unpleasant and in the worst cases can actually be deadly because our body has a limited ability to cool itself under very hot and humid conditions. But what I'm actually going to talk about today is the flip side of that coin, which is hot, dry conditions. And these are conditions, if anyone is also someone living in the West, you probably are familiar with red flag days. Those are the days that are hot, they're dry, and they're windy. And they can lead to very high probability of extreme wildfire conditions. And then overall, plants in the biosphere tend to struggle a lot during hot, dry conditions because there have been a lot of demand for moisture from the atmosphere. It can desiccate the vegetation very quickly. So the scientific context, and this will kind of feed into a mystery that we're still working on resolving, is that climate models and some developing theory broadly suggests that specific humidity, and that's a measure of literally how much moisture is in the atmosphere, will tend to increase globally, including over land. So that's just shown here in a nice figure from a Chadwick et al. Paper in 2016. This is an average across all CMIP5 models, and the relevant thing is just that this whole map is blue. Everything is getting more humid over time. If you were looking at individual ensemble members, you would of course see a little bit more variability, different behavior across ensemble members, but overall climate models pretty consistently say things should get more humid with warming. That's because a warmer atmosphere can hold more moisture. We have all these oceans around that will happily evaporate their moisture. And so we should, in some sense, just get more moisture in the air as things warm. So with that idea, we then asked a little bit of a more specific question, which is how is the distribution of humidity changing conditional on temperature? So if you think about temperature on a given day being either hot or cool, is humidity changing the same way across all of those days? So just showing that kind of schematically here, you can imagine that there's some past or historical joint distribution of temperature and humidity that I've shown here in this blue blob. And then you might expect that in the present or in the future that distribution could change in some number of complicated ways. So in this case, I've shown that temperatures are getting warmer, but maybe humidity is increasing and increasing the most at the hottest temperatures, something along those lines. We developed a model that can kind of broadly summarize these changes in the distributions that models humidity conditional on temperature. I'm going to skip over the statistics of that for the sake of this talk, and then just focus on a single result, which is looking at how humidity is changing conditional on the 95th percentile of temperature. And I'm going to talk about that as basically how humidity is changing on hot days. So if you do that, you can go from this complicated 2D view to a 1D view, where you look at how the humidity distribution is changing as on hot days from the past to the present or past to the future. And then I'm specifically going to focus on actually those driest conditions. So on days that already had low humidity on hot days, how that humidity is changing. That's shown here. Each of these points are, again, station measurements from the Integrated Surface Database data set. As far as I know, this is the only in situ measurement of humidity that's generally available. And again, we have the same issues I referenced before, where these stations are, of course, not equally distributed around the world. The model that we're fitting is a little bit noisy. And so each of these solid dots is a case where our trend is identified as significant, and the crosses are places where it is identified as not significant, but there is kind of a lot of noise. So that's why a lot of these are not necessarily coming out as significant at a single location. But I want you to focus on basically a broad scale structure of how humidity is changing on these hot days. And specifically, I'm highlighting with these boxes here that in places that are in more semi-arid regions across the subtropics, where you tend to have subsiding atmospheric circulation and overall climatologically dry conditions, we're not seeing this increase in humidity that we kind of thought we'd get from our climate models and that we thought we'd get from our theory, but rather we're seeing decreases in humidity that are shown in these brown dots. And I will say, and I'll show this for a specific case study in a moment, that these decreases tended to be greatest on the hot days. So there seemed to be a larger impact on hot days that were already often quite dry, that you're seeing these reductions in specific humidity. So to understand why, we focused on a slightly easier problem rather than looking at this whole global picture, although we still hope to do that. We zoomed in on the Semiarid Southwest, which I've outlined here with this black contour or black outline here. Each one of these dots is again one of those stations that I showed on the previous plot, and the color is again looking at the changes in humidity on those hot, dry days. With a few exceptions, what you see are a pretty deep brown color across all of these dots, meaning that we're seeing a consistent drying signal in this region. And it's actually quite significant. So if we focus on, for instance, California and Nevada, where the signal is the strongest, and if you look at what specific humidity is on hot days climatologically, this reduction is about 1/3 of that value. So you're going from already very dry conditions to reducing that humidity by a whole third. So these are getting to very, very dry conditions, again, can be very detrimental for things like wildfire. And then, as I mentioned before, we saw this in the global picture as well. The decreases in the humidity tended to be the largest at the hottest temperatures. And so what's shown here is the temperature percentile before we've been talking about only those hot days up here at the end of the plot. And on the y-axis here is, again, the change in humidity on those days. And each one of these gray lines is an individual station, what our model has found for that station. This black line is the average across all of those stations in an area weighted sense. And what you can see is if you're at these lower temperature percentiles, so your colder days, you actually see an increase in humidity on those days. Whereas as you get to the hottest temperatures here, you see the largest decreases in humidity. So we do see this kind of temperature dependent reduction in humidity on hot days. So we next want to understand why. In this analysis, the humidity analysis should say before is all using station data, but in order to get at other variables in this analysis, we entirely drew on the ERA5 reanalysis, which showed a similar behavior in humidity to what we saw in the station observations. And what we found overall is that decreases in humidity, both in terms of the interannual variability and the trends, could be largely explained by decreases in evapotranspiration. That's shown here with this composite plot. This plot is showing the differences in evapotranspiration on years that had a lot of hot, dry days versus years that didn't have very many hot, dry days. And we can see on those years with hot, dry days, we had pretty substantial low values of evapotranspiration across the whole Western US. And so we're seeing kind of primarily a land surface driven impact on humidity. We wanted to understand what the basis was of that decrease in evapotranspiration during the summer. And overall, we found that it was a function of two ingredients. One was basically how much moisture you went into the summer with, which we summarized by the June column soil moisture. And the other was how much rain you got during the summer, which can, of course, add soil moisture and therefore allow for more evapotranspiration in this region, which is quite dry. And we asked how this stuff is going to look in the future. So are we going to have more of these hot, dry days, or are things going to get kind of humid the way that we would expect from the climate model simulations? And unfortunately, what we found is that the future is basically uncertain. So what this plot shows is across CMIP 6 models, the trends in June column soil moisture on the x-axis and the trends in summer precipitation on the y-axis. Almost all models project that that June soil moisture, which is mostly a function of what you get in the winter and the spring due to precipitation and evapotranspiration, are going to decrease. But a lot of models suggest that you're going to get more rain during the summer. So a lot of things are above the zero on this y-axis. And the result is the color, which is basically how soil moisture is going to change in this region during the summertime. That's a strong control on the evapotranspiration. And what you see is basically it's a mixed bag. So depending on that balance across models of how June soil moisture changes and how summer precipitation changes, we could see the signal kind of continue into the future, or we could see it switch if we saw a large increase in summer precipitation. Okay, and then finally, the future work is really trying to understand why climate models don't capture this type of signal. And what's shown here is just a figure that actually looks at this signal more broadly. So rather than focusing solely on humidity trends in these hot, dry days, it's looking at humidity trends across arid and semi-arid regions globally. And we're conditioning on places that have a around zero trend in precipitation to not confound the likely unforced trend in precipitation. So what's shown in black is what we see in ERA5, where overall you see more or less no trend in humidity in places where you haven't seen precipitation trends. Whereas climate models, again, show overall this increase in humidity that's pretty consistent with Clausius-Clapeyron. So this model observation difference is going to be summarized in a paper led by Isla Simpson that should come out relatively soon in PNAS. But we're still working to understand what's going on in the climate models, so they all show the signal that is so inconsistent with what we see in observations. All right, so let's conclude with a few take-home points, just summarizing what we've seen so far. Northern Hemisphere summers are mostly shifting towards warmer conditions without clear evidence of kind of changes in weather variability that cause changes in variance. So we can mostly understand changes in extremes by basically this shifting behavior. That seems to still be even true, even if you look at things like the 2021 Pacific Northwest heat wave, as long as you account for instance, the climatological distribution of temperatures at a given location. And then looking at heat waves more broadly, we see this interesting decrease in humidity on hot days across the globe's semi-arid regions with implications for plant mortality and wildfire risk. And we've done a case study in the Southwest to argue that this is mostly due to decreased winter moisture. And on the bottom here, there's just some contact information. Before we go to questions, I just want to acknowledge funding from the National Science Foundation and the David and Lucille Packard Foundation. And then a shameless ad here that I am hoping to recruit 1 to 2 graduate students and a postdoc into my group. So if you're excited about these questions, feel free to reach out. So thank you so much for your time, and I'm happy to take questions as we have time.
Thank you, Professor McKinnon. That was great. So if anyone has any questions, you can go ahead and unmute yourself now, or you can raise your hand, or you can leave a question in the chat. Go ahead, Dan.
Well, thanks so much. Wow, what a terrific talk. This is Dan Kirk-Davidoff. I'm an adjunct here at Maryland, but my day job is at the Electric Power Research Institute, where we're working on providing climate guidance going forward. And this is like really, really important stuff for us to be taking into account. One quick, obvious question is, this is what I would anticipate that the answer is yes, but I'm wondering about wintertime low temperatures. Have you looked at those as well? And is the signal there also consistent? Because there's a lot of chatter about weather weirding and so on, and there's a lot of folk wisdom going on about, extreme events, extreme cold events like the Texas 2021, and whether that's just consistent with a shift in means, or if there's some broadening of the distribution going on. Very interested in your thoughts on that. Thanks.
Yeah, great question. And there actually is a great paper led by James Screen on this, showing that actually what you see as the climate change signal is the opposite of what you're suggesting, which is that the coldest wintertime temperatures tend to be warming at a more rapid pace than the middle. And that's because a lot of those cold winter temperatures, of course, are from air from the Arctic, and you're mapping that onto a polar amplification signal where the Arctic is warming much faster than mid-latitudes. So that's a case where you don't see the shift, but mostly what you see is actually a contracting of the distribution, the loss of those really cold winter days. And I will say, that's what you see statistically, and that is my expectation of what kind of the true answer is. However, I will say, it's important to, I think, always be really humble when we are working with observational data. I love to work with observations. I think that's, such a valuable record, but internal variability is huge. And so, all of these things I'm saying could all come with the caveat that it's totally possible there's something more complicated and nuanced going on that is hard to see in the data. But I think that's why it's really important to, of course, complement all of this with really basic understanding of the physics. And if we had, I don't think we do, but if we had some, well-validated physical argument of why you'd expect more winter storms, then I think that could help push you in the other direction. But I think that we don't often have those. And so, we have to be a little bit humble about what we can see in the data, and then, use other pieces of information to get our whole narrative together.
Thanks so much.
I also have a chat question. I'll just read that out loud. So, should we be identifying stations/regions which have a distribution that are more prone to extreme heat waves?
Yeah, I guess the should we, it kind of depends who the we is, but I do more or less agree with this point. So as you recall, when I, showed these made up distributions at the beginning, in the Pacific Northwest, and again, this is made up data, let me be very clear, this is just a gamma distribution, but, in the Pacific Northwest, we kind of were living in this blue distribution world where you do, basically have physical processes that can lead to these unusual but very extreme events. I think it's an interesting question that we're working on in my group of, can you identify in a general sense what those processes are? But the relevant thing is that, in some sense, when you get these tail events, you're maybe just getting them a little bit more likely at these certain locations because you're in places where you have these positively skewed distributions that allow for those very extreme events. And so I think it is a relevant framing to say, where should we expect to see a 4 sigma event? Where should we expect to see a 5 sigma event? And there actually was a nice paper recently led by Vicki Thompson where she did something similar with generalized extreme value distributions. But I think that there's more work to be done in terms of what we need to be prepared for passing on this information to people who are making decisions in terms of, the most extreme events that we might expect to experience.
Thank you. Taryn, you can go ahead.
Hey, Karen, that was really interesting, especially as someone who lived through that heat wave. I was curious, so it seemed like a lot of the numbers you were looking at were kind of June, July, August, or seasonal maxima, and I'm wondering if it's possible to drill a little deeper into saying, like, how weird is it that that heat wave occurred in June rather than in August, which is typically much warmer in the Pacific Northwest?
Yeah, so two important points there. First is that, and I apologize if I didn't emphasize it enough, but all of our analysis of the Pacific Northwest was focused on the 30 days centered on June 30th. And so we did in that analysis think about things only in the context of anomalies from where you are at the seasonal cycle at that point. However, as I kind of alluded to early studies that were trying and sometimes struggling to get these types of events in climate models. And in some cases, they could get them in anomaly space, but really only in August. I think it was generally harder, if you will, to get them in June. And I want to emphasize that's not just because of the seasonal cycle. So in all of these analyses, we're usually removing the seasonal cycle. We're already accounting for the fact that it's climatologically a little bit cooler in June, but then thinking about, what are the processes that are causing heat waves? And it did seem the climate models could make it be more likely to get those types of anomalies later in the summer. However, our whole analysis was focused on that earlier period. So when we did see those heat waves in the climate model, that was happening within 15 days of June 30th.
Okay, cool. Thank you.
If you have any other questions, you can raise your hand or chat or just unmute. Give me another minute or so to think. Oh, here's a chat question. A quick question about the first slide. What is the data source, air temperature, or land surface temperature for the temperature trend analysis?
I think probably for this type of analysis is my guess. So yeah, there's different data sets that are coming in here. This is all Global Historical Climatology Network daily data. And that's true of most of this first section, although in this case we used ERA5 reanalysis, and we'll be adding in the station data analysis once we publish the work.
Great, thank you. Any other questions before we finish up for the day? Okay, well, unless I am interrupted, which feel free to do so, I think we can conclude today's talk. Thanks so much for everyone for coming, and thanks so much Professor McKinnon for giving us this talk. We will continue with our seminar series next Monday. We have an in-person seminar, so we look forward to seeing you then. Thank you, everybody. Have a good rest of your day.
Thank you.